Hello and welcome. Today, we're diving deep into one of science's biggest mysteries, dark matter. It's thought to make up about 85% of all matter in the universe, yet we've never directly seen it. The quest to find it hinges on direct detection experiments, which are designed to spot the incredibly rare interactions of dark matter particles with ordinary matter inside highly sensitive detectors. Imagine trying to catch a ghost. It's that challenging. There are several leading technologies in this hunt. Noble liquid detectors are some of the most sensitive, especially for popular candidates like WIMPs. These use large tanks of liquefied noble gases, such as xenon or argon. When a particle interacts, it causes a flash of light, called scintillation, and releases electrons. By measuring both, scientists can try to identify a dark matter event. Think of experiments like xenon, LZ, and Panda X. Another key approach involves cryogenic crystal detectors. These use crystals like germanium or silicon, cooled to temperatures just fractions of a degree above absolute zero. An interaction deposits a tiny bit of energy, causing a measurable temperature blip. These are particularly good for searching for lighter dark matter particles because they have very low energy thresholds. CRESST and super CDMS are examples here. Then there are crystal scintillators, like the sodium iodide crystals used in the DAMA Libra experiment, which famously observed an annual modulation in their signal, hinting at dark matter, though this result is debated. Bubble chambers, like PICO, use superheated liquids where an interaction can form a bubble. And new quantum sensing techniques are emerging, aiming to detect even lower mass dark matter, potentially by sensing tiny vibrations caused by particle interactions. Some are even working on detectors that could tell us the direction dark matter came from, which would be strong evidence. But the challenges are immense. Firstly, dark matter interactions are expected to be extremely rare, maybe only a handful of events per year in a huge detector, or even none at all. Secondly, there's a constant barrage of background noise. Cosmic rays from space are one source, which is why these experiments are built deep underground. Radioactivity in the detector materials and surrounding rock is another. And then there are neutrinos, particles from the sun and elsewhere that can mimic dark matter signals, creating what's known as the neutrino fog, an ultimate background for many searches. Dark matter particles are also expected to deposit very little energy, requiring incredibly sensitive detectors. And because we don't know exactly what dark matter is, we need a variety of experiments, as different technologies are sensitive to different types of dark matter particles and interactions. Making these experiments bigger and more sensitive is also a huge technological and financial hurdle. Despite these hurdles, the search pushes forward. Progress depends on innovating new detector technologies, finding better ways to shield from backgrounds, and using sophisticated data analysis. The goal is to finally understand this major component of our universe.